Hola, ahora sí. Sí, okay. Thank you for the advice. Uh, okay, I'd like to show you an application to neuroscience, or more than neuroscience, to epilepsy or epilepsia. In particular, I want to show the case of tonic-clonic epileptic seizure, that this is one of the most traditional, or showing, if you see somebody have a seizure attack or seizure episode, is typical from this kind of things. Let me see that where I have. Just a few minutes more. Oh, no. Okay. This is the recording, which is the tonic-clonic epileptic seizure. How you understand? Well, this is divided into uh, different part of symptomatology when you have it. That is, the tonic part is when the person have a rigid position, and after some seconds or some minutes, they started to convulse. They started to have the typical tonic. The tonic is very hard, it's and then it started to make this kind of thing. The interesting thing in the epilepsy is that normally the epileptic focus is in each person that have this problem is always the same. Yeah? Normally, there's an epilepsy as the lobulo temporal, uh, especially the focus is centered in the hippocampus nucleus or amygdala. And this is this part of in the middle of the brain. And in this case that we want to show you, this is the record. There is with this is undertaken. This record undertaken under video because normally it's just for to know when the seizure start and when the seizure finish. And we can say in this case that okay, this part of the pre-crisis until about 80 seconds. As this is the second and go to one. So at 80 seconds started the seizure, which is very slow, increase a little bit the amplitude with a little bit of oscillation. And after that, this is the part that if you want to say, when is the start the tonic and the clonic part? The transition between the tonic to clonic. I can say nothing about that. Just looking the activity of in this record. And finally, around 180 seconds, or 60, I don't know what, 150, the seizure of 55, the seizure ending. How we can understand this kind of transition? Well, the first thing that we must to do, okay, this is in the in C4. This C4 is you have the 20 the external electrode. A C4 is corresponding to the, or is put in the middle of the two hemispheres, and C4 is something central for from the right side. Yeah. just for to know. The problem is, in this case, is that from somewhere or some methodology, I need to eliminate the component, the muscular component, because when they have this tension or the tonic part or the other, we have a contribution of the brain activity specific that we want to study and the muscular activity. Muscular activity is around 15, 20 hertz, and that's how we can eliminate or delete this activity from our signal in order to study what happened specific with the other signal. This can do it using wavelet, orthogonal wavelet, and we can eliminate the, we can, I think it's, I have the, I don't know, okay. This is eliminated the orthogonal wavelet. We can decompose a spline cubic. That this is the, in the particular, the mother wavelet that I used in this case. But you can use orthogonal wavelet because this orthogonal wavelet, anyone that you choose, except the hard, because this is very, very simple, is that when you divide it from the different frequency band, you don't have a very limited in the frequency and in time. This is quite convenient when you have a noisy signal and you want to eliminate some part of the signal because it's not interesting in your case. In the case of epilepsy, this is perfectly to do it. By another hand, this kind of epilepsy was first described by Gaston and Broughton, and they found out something interesting, that they say that after a few seconds after the seizure start, they says appear epileptic recruitment rhythm about 10 hertz. That is characteristic of this kind of seizure. This is some information about the epileptic focus and how the epileptic focus act is the epileptic focus start the seizure, but they have a recruitment activity of the rest of the neuron and propagated to the rest of the brain. Yeah, this is the main idea that you have how is the epileptic focus. It's a epileptic focus is something like an oscillator. Why this kind of oscillator appear? Well, some problems with the neurotransmitters and so on, but and after some time they disappear. They left to be activity, and the rest of the brain goes to the normal state. Yeah. Well, and then we divide the frequency band in the delta band is between 0.5 hertz until 2 or 3 hertz. Then the theta band is in between. The alpha band is in between 8 and 12 hertz, and the beta and gamma band are the higher frequency. That this is that we identify that this is corresponding the frequency band that we want to eliminate. This can do it easily using orthogonal wavelet transform for the discrete case, of course. And this is the in this case, I make a graphic again of the seizure, how we try to analyze with in our case. And we see, if I say that something about, we can distinguish when the transition between tonic to clonic appear? No. I just looking at the signal, we say, okay, this is something that started, okay, that by the amplitude continue, and something around here is the transition, and we want to see if we can say something about this kind of transition. What we can do it, I mean, that I say in the previous talk, when you have a time series, you want to associate it a probability distribution to this probabilities. And what we can do it, I use the decomposition, the wavelet decomposition, and let me see to see that have a article. Yeah, it is okay. Even when I represent here this scheme, but the idea is exactly the same. You have the EEG. In this case, okay, you have an event-related potential, but the idea is the same. I make the wavelet transform, orthogonal wavelet transform, and obtain the delta band, theta band, alpha, beta, and gamma, the different frequency, the different resolutions that you will have. We associated again the resolution in each frequency band is a little bit changed, but we need to define a time window that in order to have evaluate the energy. We can evaluate the energy like in Fourier or something like this. Is simple. Take the wavelet coefficient corresponding to the different frequency band. We elevate it to a square, and this can give me, ¿dónde estamos? Se me perdió acá. We can evaluate the energy in this frequency band of interest, yeah, and like a square of the energy. If I sum all the energy that I have, I can give you some information about the relative wavelet energy. As mean, we sum all the different frequencies in the window that I consider, and then I can do it. I am in conditions of evaluate the Shannon entropy or whatever other entropy that I like, the complexity and so on. Okay? Okay. This is, we say that this is the energy decomposition for the signal. The band that I consider is are these. This means beta, alpha, and so on, beta, delta. Beta, I don't include it because this is associated with the muscular activity and is not important in the case of in the frequency of the band we want to see. This is the pre-crisis, and I say the seizure start around 80 seconds, and in the pre-crisis I don't see a dominant or any of the frequency band. These all are mixed. The shadow that I present here is almost we expected to appear the epileptic recruitment rhythm proposed by Gaston and Broughton. Of course, I forgot to say, how we can eliminate the activity of the muscular activity? Well, this record normally are used, or when Gausto and Broughton described it in the 60s, or in beginning of the 60s. They take it, the epileptic person have a curare in order to have with also with artificial respiration because he's not he died, and but we see that a clear how the in this case this is alpha and part of the alpha activity, and you see that this is a very sharp decreasement in the activity of delta and theta. And this is the frequency band, and this is just that we are describing like the appearance of epileptic recruitment rhythm. Uh, Also, we see that after some few seconds, around 10 seconds, or 10 seconds, the epileptic seizure start, appear the epileptic recruitment rhythm in this shadow representation, that this is mainly the activity in order the 10 hertz, yeah, we can. After that, appear the epileptic started to normal ending and started to normalize, and again after that the seizure ending around 150 seconds. Again we have something similar to the pre-crisis. We want to describe this. Okay, this is the frequency band that I have. We can see, we analyze 20 epileptic, 20 patients with a different kind of seizure, and we see this is pre-crisis. That is, no, it's not dominant, this is relative, before that. It's just for to show that effectively this epileptic recruitment rhythm appear in all the seizures that we analyze. As you can see, there were the different patients and so on. And what happened? We evaluated the entropy. A good thing is, okay, in the pre-crisis, we have not a dominant frequency band. This is almost frequency, but during the crisis, the crisis of the seizure, we see, okay, this is with the different entropy formulations. Q equal 1 is the Shannon entropy that I described previously. The other are the Salis entropy and Renzi entropy with different Q values. And we see that, again, we see that during the epileptic recruitment rhythm, we see that is a decreasement around 120. We see this is appear at some kind of transition between one state, one behavior to the second behavior. This 100, around 120 represent me the transition between tonic to clonic behavior. This is something that just look into that I showed you previously. We can see here in the where 120 is Here, I don't see nothing that happened. There's a lot of oscillation, but nothing more. But this is the new information that we have. And we see that also at some peaks and in activities here that is mark how uh, the clonic epileptic or the end of epileptic recruitment rhythm appear, and again a new peak around marking when the seizure ending. Okay, and what happened with the complexity? In the complexity, we see again the complexity in the previous state and the pre-crisis state. I don't say that is almost very low because it's not a dominant frequency, and all the frequencies, the wavelength band usually describe the activity in the brain are almost in the same behavior or the same intensity, but again, if we see that this in the part of describing the epileptic recruitment rhythm, this is a specific frequency will be dominant. This is around 10 hertz that I say, and this is when we have see here, and this is again we come the description with the different Q values. Remember that the Q equal 1 is the Shannon entropy and the Shannon complexity with the Jensen-Shannon, okay? What more we can see, how we can understand this behavior, this appear of the epileptic recruitment rhythm, is if we think that that the epileptic focus act like a global pacemaker, they are recruitment population of neurons around here, and extended and then progresses to the rest of the brain. Even here, we are only analyze this, but you see that we can see from the different frequency, the different electrode that we say. How this is ending? Well, the problem is how the seizure ending. The seizure ending because they are forcing in some way that all the activity in the brain or in the different frequency band must to go with the frequency of the epileptic focus. They are coupling and synchronizes. Maybe we can study the synchronization with the different areas. We don't do it, but this is some possibility. And ending because to respond, all the rest of the brain neuron respond that's the frequency that they impose the epileptic focus is at the beginning is very high, and then the frequency of the epileptic focus is very high, and then the muscular activity are not coupling and can, because this is understanding how we say, okay, this is the tonic part, this is rigidity. And after that, when they started to decrease, because the activation of the neurotransmitter also they started to decrease, and they don't produce with the same value or the same velocity for the rest. They started to decoupling, and then started the response in synchrony with the epileptic focus, and finally the epileptic, the seizure ending. Like the neuronal activity are target boring to respond with this frequency activation. Yeah, but this is interesting, and also again we coupling again, and we see in the post seizure, that is again we recover the normal activity, because this is correct. This is something that we see, except the person that when they have not a seizure or some activity in the epileptic activity, this is normal. And this is why we can understand how this is the behavior during this kind of epileptic seizure. We can do it here. Is the entropy complexity plane, of course. We can do it. And we see for the different pre-crisis, during the seizure, and after that. And here in the graphic below is, I lose the pointer. I see that this is started almost not significant, but this point, this is when it goes, and then return to here. This is the point that mark how this is the maximum, the transition between tonic to clonic activity or phase, or seizure. Well, this we can see. Well, this is how we finish, how we can show, how you can analyze with wavelet, because we separated, and how we associated the probability distribution to the wavelet energies, and we can use it in order to see what happened in the seizure. This is some applications that I left. How we can do it, entropy, complexity, and Fisher information in the case of complex network. Who are interested, you can see this in reality it is only this paper. This is from almost 2 years ago. The corresponding, I put just, you can access this. The other is some correction for you need to order again previously that your network, will consider you need to order by the intensity of the nodes, but it's nothing. You can see directly here in this paper. And in this paper, I don't found how to include the figure, but you can define the different kind of complex network and how we can classify in the Shannon-Fisher plane, and we can identify the different type of complex network. I think it will be interesting just if you understand how to apply this, and this is just an update. And okay, with this, I think I finish my presentation. Questions about this kind of thing? Other applications but my co-authors was interesting that we use the same in the case just for demonstrate that the brain in men and women are different. In the analyzing the different brain activity during the sleep and during the using intracranial activity, but they say me no because you can talk about this because the paper is not published yet, but okay, I say, well, okay. And you that they make the main work, I can must respect, but it is a difference in the different areas using intracranial brain activity. We can say just an advance of the new papers that will be seen. If you are interested, I can send you when they will be published. Yeah. Okay. This is the end of my talk. If you have some question, we can continue with the activity. Yeah. Yep. Ah,
For what I gather, you're looking for entropy changes in clonic and tonic events, right?
sí.
So, is there a way to apply the same or sort of similar techniques for interictal spikes or
Yeah.
other?
Yeah, you can do it. I mean, in the interpipe, you don't need you don't need to filter the signal because I need to filter in this case because I need during the part where the rigid tonic. Again, I have a muscular activity that they mixing or add to the brain activity. This is why when the seizure started to propagate, I recruiting more and more populations or population of neurons, and they finally finished because they started to discoupling at the end. But you can do it in the case of you have a very noisy signal, as I say in the previous case, as you have a very noisy, they move the activity during in the entropy complexity plane because as you are adding some colored noise that could be uh, a way to delete this colored noise or whatever you don't want to be included in your analysis. Yeah, but you can do it. This is no problem. Uh, there is many different ways to analyze the signal, to associate a probability distribution to the signal under analysis. Especially if you take the time causality, this will be the better result, because in the other case, you are mixing, you lose a part of the information. This is something equal what happened with Fourier. When you make a Fourier analysis, you don't know at which time the frequency appears. We see some change in the frequency, but don't know when. And here, this can do it with wavelet because give me some information when and which frequency band activity. And this, we can do it in this way. And using, of course, orthogonal wavelet, this giving without overlapping between the frequency band, the proper frequency band that we are analyzing. Yeah, that's okay.
Any more questions? Well, thank you very much, Osvaldo.
Okay.
And, so, who's the next?